Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our third lecture covering material from Chapter 8. We begin this lecture with a theory that we're going to use to help us predict the shape of molecules, and it's called VSEPR. The scientists actually call this VSEPR. It doesn't VSEPR. It's an acronym for valence shell electron pair repulsion. So this is a model to predict the shape of molecules. And the basic idea behind this model is that our electrons, even if they're bonded, so if they're bonds or if they're lone pair electrons, when they're in the valence shell of an element, they're going to repel each other and try to be as far apart as possible. So these arrangements will, arranging these electrons as far apart as possible, ultimately creates the shape of our molecule. So we've got 5 what we're going to call electron pair geometries shown in this slide. And we're going to come about these geometries by counting around the central atom. What we've made up this term domains. So a domain is either an atom that's bonded to the central atom. Doesn't matter if it's a double bond, a triple bond, a single bond, it's just one domain. Or a lone pair of electrons on the central atom is considered a domain. So I'm looking at the one that says linear here. I've got a central atom and I have 2 domains. So when we have 2 domains, the way we can put these electrons in these bonds furthest apart would be 180 degrees apart from one another. And this makes sense. This would result in a linear or just like a straight line shape for our molecule. And the example they're showing here is BeF2. And remember, beryllium, that's one of the exceptions. It's just formed the 2 bonds. The next one, 3 domains, we call this trigonal planar. So this is flat. It's hard to see in 2 dimensions, but it's flat like a piece of paper. And these atoms are placed 120 degrees apart from one another. And this is the arrangement that will put these as far apart as possible. Still believable, really. So we've got 120 degrees. If we think about a full circle being 360 degrees, I can divide that by 3 and get the 120. That'll help me with that bond angle. Help me remember that. This example, 4 domains. Notice in each of these examples we don't have lone pairs, and lone pairs would also count as domains, but we'll get there. 4 domains, this is where we start to get 3-dimensional, and we get this tetrahedral arrangement. It's called tetrahedral, and the bond angles here are 109.5 degrees, and you'll just have to take my word on that one. And this is getting a little more difficult to do conceptually, but think about this in 2 dimensions. If we had a central atom with 4 bonds coming off of it, the furthest apart we could get them would be 90 degrees. So we could put them like on the, like to the north, one to the north, one to the south, one to the west, one to the east, and we'd be 90 degrees. But this arrangement, when we go 3-dimensional, we get 109.5, which is further apart, more desirable according to VSEPR. 5 domains is what we call trigonal pyramidal, and or bipyramidal, I should have said. So the trigonal, we've got the tri up there, makes me think of tricycle, 3 wheels. Well, this has 3. It's a pyramid with 3 sides, and this is the top of the pyramid. And we also have a pyramid down below, so that's why we call it bipyramidal, trigonal bipyramidal. And the last one here is the 6-domain example, and we call this octahedral. And at first, 6 doesn't make you think of octa being 8, but if we look at the faces on this, the way this is set up, if we had a face, they're trying to show it here, there'd be 4 faces on the top and 4 on the bottom. So that's where we're coming up with the octahedral. So let's look down here below. We've got this example here, the NH3, and this does have a lone pair. So this has 4 domains. There's 1 with the lone pair and 2, 3, 4 with the hydrogens. So the electron pair geometry, is tetrahedral, 4 domains. But our molecular geometry, like what we're seeing when we look at this molecule, these electrons they're taking up space, and what they've done is they've pushed these hydrogens into these positions, into this tetrahedral type base. But when we look at the molecule, we don't see this. We just see the nitrogen and the 3 hydrogens, and it has a special name. It's called trigonal pyramidal, and again, the trigonal with the 3, and pyramidal, kind of a pyramid shape. So we've got another structure over here. It looks like it's just a made-up structure. It's not that great. But point is, we've got some atom here, not carbon, but we got an atom with a lone pair, and then we've got 2 bonded atoms. So we'd have 3 domains here. This would be a trigonal planar for electron pair geometry. But our molecular geometry, if we didn't look at this, it's called bent, and that bond angle would be 120 based on the trigonal planar. This is a little bit messy slide, but we're just saying here our electron pair geometry is determined by the number of domains, and again, we count lone pairs of electrons on the central atom only. So I've got 2 on this oxygen, and then the bonded atoms. So I've got hydrogen is 3, hydrogen is 4. I've got 4 domains on this. So we're just looking at the atom. If this were a double bond, that doesn't make it 2 domains, still 1 domain. We're looking at the number of atoms here. And, just kind of some vocabulary, I guess. So we're talking about electron pair geometry and then molecular geometry. Well, the molecular geometry is the molecular structure, and this is what we're looking at when we're just looking at these atoms. So this one, with the water is bent, in the angle here, it's actually slightly less than 109.5 because these lone pair of electrons, they take up a little more space than a bonding pair. So they kind of bully these hydrogens down a little more than the 109.5. There's a couple things worth noting here is when we get up to the trigonal bipyramidal, so this is 5 domains, if we have a lone pair, it's going to reside on what we call equatorial positions. So this is the best I could do to draw this, but I've got 5 domains. So I've got a central atom in here, and I've got two domains kind of along this straight line, and then I've got 3 more kind of circling this. And I like to think of this as like the inside of a globe, and this is my axis, and this is my equator. And these are actually called equatorial positions, and this is where the lone pairs will go, and these are called axial positions. So on this molecule, so if you have lone pairs, they're going to go on the equatorial positions. In the octahedral, and another lousy drawing here, here's my octahedral. I've got a central atom that I didn't draw, and I've got my 6 domains, 1, 2, 3, 4, 5, 6. If I have a lone pair of electrons, it can go anywhere, but the next one will be completely opposite of it. So I tried to show that here. I've got a pair of electrons. I just represented that with E minus. So there's the first one, and then the second one, it's very important that it's directly across from it. So it would be in this position. This, going back to my trigonal bipyramidal with 1 lone pair of electrons in the equatorial position, let's look down into this area. And this is what it would look like. And we actually call this seesaw, and it looks a little bit like a seesaw. So this is the equatorial positions here, and there's my axial positions. Now, if I had 2 lone pairs on this trigonal bipyramidal, so take away this and put another electron there, you can see the resulting shape, and it's literally called T-shape. So those are the molecular geometries. So we've got 2 geometries going on, electron pair geometry and molecular geometry. Now, if there's no lone pairs, they're exactly the same, and that's a good thing to know. So we've got some examples here. We did all these in class, but I've got one here I can show you. So we have, well, it looks like we have BH3 here. So we draw our correct Lewis structure. I've got 3 domains. This is trigonal planar. The angles are 120 degrees. And because there's no lone pairs on this one, the electron pair geometry is the same as the molecular geometry, and that's called trigonal planar. So we do have a handout for this, a kind of a sheet that walks you through the process. Hopefully you can get your hands on one of those. You certainly want to try practicing these. So we've got a giant molecule here, and it really has multiple centers. This is not a terminal atom, right? It's bonded to more than one thing. So this is a center. This one that's a central atom. This is a central atom. Lots of central atoms. So a lot of times they'll number these and they'll say, what's the geometry around this atom? Okay, so it's carbon. And so how many domains do I have? 1, 2, 3. 3 domains. So this is electron pair geometry is trigonal planar. I know these bond angles are 120. They don't look like 120 the way we draw this. So that can be very deceiving. Maybe the question would ask, what are the bond angles? And they look like 90, but they're not. We'd have to know that was trigonal planar. And the molecular geometry is the same because there's no lone pairs. How about this nitrogen? I've got 1, 2, 3, 4 domains here. So my electron pair geometry is tetrahedral. My bond angles are 109.5. My molecular geometry is different because I do have a lone pair of electrons that we're not looking at when we're looking at the molecule. And so my molecular geometry is called trigonal pyramidal for this one. When we have a molecule or even a bond, the electrons are kind of being pulled on by the elements depending on their electronegativity. So if we had a real high electronegativity, like fluorine does at 4.0, and that's bonded to a hydrogen that has an electronegativity of 2.1, we have, this is kind of a heat map showing where the electrons exist, and they're closer to the fluorine. And we call this a polar molecule because it has an uneven distribution of electrons. Our diatomic elements will be nonpolar because we would expect that the electrons would be evenly distributed because the electronegativities are the same for both of these. So we can look at bond polarity, and bond polarity is just looking at the electronegativities of the two things that are bonded. And the bigger the difference in those electronegativities, we can say the more polar the bond is. Now, most of the time, your nonpolars are going to be diatomic elements, but there are a couple elements that have the same electronegativity. I think carbon and sulfur have the same electronegativity, so a CS bond would be a nonpolar bond. This is just a periodic table showing the electronegativity values, so you're going to be provided with one of these if you're going to have to do anything with electronegativity or polarity of a bond. For a molecule to be polar, we have to look at the shape, and we have to have an unequal distribution of electrons. And we can see, like in this example, we've got this ammonia. So we've got 3 hydrogens, and we've got this lone pair of electrons. It's not a symmetrical situation. So we have what we call a dipole, and this is a polar molecule. The BF3 can be, or BH3, or B anything 3 that it's bonded to, can be especially tricky because it doesn't appear to be symmetrical with 3, but if those atoms are all the same, it is nonpolar. So we've got some steps to predict if a molecule is polar or not, and we're really looking for symmetry to tell us if it's polar or not. So we've got some examples here, or some practice. You should be able to do these. You're going to draw the Lewis structure, give the electron pair geometry, the molecular structure or molecular geometry, and indicate if it's polar. And I've got the answers on the next slide for you. So if you want to pause this and write these down so you can work on them, that'd be great. You definitely want to be comfortable with this before heading into the next lecture. So here's your turn to see the answers. I appreciate you watching. Give the video a thumbs up and subscribe if you want to see more on the Professor's DuBois channel.